Okay, before we start, any questions regarding the assignment and everything? Okay. All right, so maybe I should starting to taking some stand-up sheet because nobody showing up. Yeah, I mean, usually I don't do that because, you're adults now. You're responsible, for your future, right? It's your choice. I don't want to be forced to do, the learning. But I think you're paying for your education, right? So not me. So anyway, so it's okay. Let's get started. So today we'll continue talking about efficient deep learning. So we are still trying to address the first challenge we mentioned, right? So how these deep learning model is able to cope with, the varying resource during the real-world applications. Just to have a very quick recap from last week's lecture, right? So we talked about efficient neural network design, right? So you have different options you can choose, right? We can using network pruning, right? Basically reduce the size of the network, and you can also come up with some strategies, for efficient network architecture, right? So that, maybe change the a conventional design like convolution or transformer to make them more computation and memory efficient. And we can also using quantization, right? So to reduce the precision of the network so that you can also gain some efficiency. Mostly very useful, right? In terms of the energy consumption, right? You should have some edge devices, you don't have a lot of power. And lastly, we also talk about the knowledge distillation, right? Basically, you can using a larger teacher network to kind of guide the smaller student network to learn very good representation. Then during the inference time, then you can only have to deploy a smaller student network. We've also talked about dynamic network, right? Because all these efficient neural network design ultimately will result in a fixed network, right? So once you pruned or your network is designed, the network architecture is fixed. But since we have application or scenarios that these resources will change over time, right? So how we are able to cope with the dynamic, resources. So that's why we want to develop some dynamic network, right? Is able to change the network architecture, or maybe change the input scale, right? If we're talking about images or videos, or we can using some quantization, right? To intelligently assign the most important bits, right? To the maybe certain layers, right? So we've specifically discussed the two papers that is in my group, right? So for the medical volumetric segmentation, right? So we can taking into account different slices, and there are different characteristics, right? So how you can intelligently apply maybe a smaller network to certain slice, or maybe a heavy network to some of the complex slide. So the next for this class, we'll talk about another challenge, right? Which is also very important, right? Because in the standard, deep learning applications, right, we are kind of following this standard pre-training then fine-tuning paradigm, right? So pre-training is basically like if we're doing a lot of image and vision applications, that will usually take an ImageNet 21K, right, pre-trained model. Then using that pre-trained model, do some fine-tuning on the downstream task. For example, we are doing medical image classification or segmentation. Right, so here, let's using medical image segmentation, as an example, right? So you have ImageNet and have a pre-trained deep neural network, and usually you have to fine-tune the model for the target domain, right? So you have a medical image training set, right? So you are using these training set to fine-tune the model, okay? So a lot of time we will do the full fine-tuning, right? Because for some of the large domain gap, right, we want to kind of tune every of the neurons, right, to make them adapt to the downstream data set. But you can also selectively tune some of the layers, right? So as we mentioned in one class, right, you can selectively maybe tune the later layer, or maybe just only tune the last classification layer, right? But ultimately, this is the the standard strategy, right? Pre-training, then do the fine-tuning. So if we want to go for the full fine-tuning, right? If let's say we want to gain the best accuracy or performance we want, right, for the downstream task, especially in the medical setting, then if we are using a very large network, right? So now we are all using the transformer architecture, right? The vision transformer, billions of a parameter, right? So you can imagine fine-tune do a full fine-tuning, right? All the parameter of this pre-trained network is going to be a lot of computation cost, right? Basically, you have to tune every neurons in this network. So there's a high cost, occur, do the full fine-tuning, okay? So for this class, we'll talk about some of the efficient strategies, right? How can we promote this parameter efficient fine-tuning for the transformer models specifically? But of course, these fine-tuning strategies can also be applied to the CNN architectures, right? Not necessarily limited to transformer, but it's just because of the prevalence of the current transformer model in the large language model or the vision domain has been widely adopted. So that's why, and it's usually come with billions of parameters. So that's make this parameter efficient fine-tuning really important. Okay. So by the name, right? So we want to basically do parameter efficient, right? So we don't want to tune all the parameters in the network, right? Maybe we only want to tune a very small subset of the parameter, so that we can still gain maybe comparable or even better performance as compared to you do the fine-tuning, full fine-tuning, okay? So that's the basic idea, right? Just only rather fine-tune the entire model, let's just fine-tune only a small amount of weights, right? So that we don't have to use a lot of tuning, incur a lot of tuning cost. And this will have a couple of benefits, right? So first is, most important is the efficiency, right? Because we are tuning only to a small subset of the parameter, so it's very fast to converge and also use less resource, right? And also, some of the practical benefits will bring is because you are not full fine-tune the entire model, right? So you don't have usually these large models are over-parameterized, right? So if you don't have a lot of downstream data, then you have a high risk of overfitting, right? Because you only have a small number of data, then you have a large network, then it's prone to overfitting. But if we only tune a small number of parameters, we can reduce that risk of overfitting. And also, it will enables the rapid adaptation to the new task. So typically, we have a couple of strategies that we can use to achieve this parameter efficient fine-tuning, right? So here, these graph shows a couple of strategies, right? So here, these blue bars here indicating this is our pre-trained network, right? Theta. We're using this theta indicating the parameters. And we want to fine-tune the model, right? Theta prime, so that it will fit or adapt to the downstream task. So one strategy is you can adding some of the tunable layers, right? So here, the blue color indicating we freeze, these parameter, right? This is pre-trained. We don't touch them, right? So we just keep them frozen. And we only add some tunable parameter, right? Maybe you can consider adding a couple of layers, right? This could be like a new classification layer, or maybe you just want to adding one more, fully connected layer at the end, right? Just to change something, right? So these new learnable parameters able to kind of change some of the behavior or feature representations is able to adapt to your downstream data, right? So that's the addition. And also you can do specification, right? So basically, select a couple of some layers specifically you want to fine-tune, right? So this is we talk about in the CNN, right? So maybe you can fine-tune only the last 2 or 3 layers to adjust the feature representation. then the initial layer, you don't have to touch them, right? Maybe basically they are, extract like the edges and corners, right? They all have some common features. You don't have to adapt those, but only adapt some high-level representation. In the transformer architecture, this can also be applied maybe in the later transformer block, right? So you don't have to do this for the entire transformer or every transformer block, maybe just a couple of layers. And the last strategy is the reparameterization tricks. So we will specifically talk about one technique falls into these paradigm, right? How we can using reparameterization to achieve efficient fine-tuning. Okay. So again, let's using transformer model, as the main backbone in this lecture. But a lot of technique can also be applied in the CN architecture. So the first parameter efficient fine-tuning technique is called prefixed tuning. Okay. So this idea falls into the first category, right? So basically, we want to add some tunable parameters, right? So to adjust the model representation, but not all the model, parameters in the model, right? We still keep the pre-trained model fixed, but we're just adding some learnable parameters. Hopefully, these learnable parameters able to adjust the representation. Okay. So these prefix basically just some tokens, right? So they can be randomly initialized, and during the training process, these learn or prefix tokens they can be learnable. Okay, so they can the network you can train with backpropagation, and the gradient will only flow back to these prefix tokens, right? Because the other layers, right? The transformer layers will keep it frozen. We don't touch it. Okay, so the gradient backpropagation will only flow back to here. But why this prefix is able to adjust some of the representation, right? Because these prefix is actually applied in every transformer layer, right? So this will participate in these self-attention mechanism, right? So you have these input, each of the layer, you append these prefix tokens to their original input token sequence, right? Then will participate in the self-attention computation, right? Those QKV matrices. And eventually, these are the learnable, right? So they will basically adjust these attention mechanism based on these learnable tokens. We call this prefix token, okay? So that's the idea. So here, just summarize the training dynamics, right? So we'll have the original model parameters remain frozen, right? Ensure only the prefix token are updated, okay? And the gradient will compute only for these prefix token, allow them to learn some task-specific representation, right? So because, a lot of the majority of the model, right, because we are learn from large-scale training, right? We don't want to change them too much, okay? So hopefully a small amount of these prefix token, right, is able to effectively maybe steer the representation to some of the downstream data distribution, okay? The next technique, which is very similar to the prefix, tokens, prefix tuning is called this prompt tuning, okay? So this prompt token is basically appended or kind of concatenated in the input dimension, right? So this is transformer for the language processing, right? So you have input sequence, all these language tokens, text tokens, then and they will go to this embedding layer, get this embedding token, right? So you basically, put some learnable prompts here, and then hopefully these learnable prompts is able to help adjust the representation, right? Compared to the previous, right? The prefix, basically you apply to different stages, different layers of the transformer block. But for the prompt tuning, right? So you basically just apply in the input. So again, right, so this is prompt tuning is very similar to the prefix tuning, right? So the majority of the model is keep frozen. There's no weights updated, and only the gradient will back propagate through these prompt tokens, right? So hopefully through this kind of small amount of prompt tokens, the representation will be able to adjust to some of the downstream specific applications. So here are some of the use cases, right? Like when it's better to choose prefix tuning or when we can choose a prompt tuning. Okay, so for the prefix tuning, it's best for in general. Okay, so this is not like the 100%, but in general, it's best for tasks require some more nuanced control over the model internal representation, right? Because these prefix tuning actually apply to all the layers, right, for the transformer block. So you may want to just adjust a little bit, right, for the entire representation. This also may be able to help you to achieve like near full tuning performance, right? Because we are adjusting each of the block by a little bit, right? So maybe this a little bit adjustment should already be enough, right? So maybe able to achieve like a full fine-tuning performance, okay? But for the prompt tuning, right, so we want to do some quick adaptation to the new task with minimal change, right? Because this is only applied to the input, tokens, right? So we only append some, prompt token in the input layer. So you can imagine this is even less tunable parameters as compared to the prefix tuning, right? And this can help us to have very quick adaptation. And we don't want to change the internal representation too much, but we just want to have a very quick adaptation. Something to consider is when you select the prefix tuning or prompt tuning is the complexity and the simplicity, right? So it's also depending on your tuning budget, right? So how much computation or memory you have, then you may have to select which one to choose, right? So in this, maybe some of the cases, you don't have a lot of computation resource for the fine-tuning, and also the task may be very similar, or the data are very similar to the original pre-trained data, right? Then maybe you don't need this kind of nuanced control over the entire network. Maybe just a small amount prompt tuning is sufficient, right? So you can choose prompt tuning in that scenario. So these methods originate from the large language model, right? So because large language model are a lot of parameters, so how we can using those to achieve efficient fine tuning, and we can also apply these technique readily to vision transformers, right? So here in this visual prompt tuning paper, they are using this kind of prompt tuning idea and apply to the vision transformer, okay? So on the left, we can see that, right? So this is the standard vision transformer process pipeline, right? So you have input images. You basically divide this image into small patches, right? So you have a sequence of patches, then you go through some embedding layer, right? So it can be simple MLP, or maybe you can using some initial CNN, a couple of CNN layers, right, to extract some features. You get this feature embedding, E0, okay? So these feature embedding, then say they propose these two strategies, okay? One is they call visual prompt tuning deep, okay? So this is more like a prefixed tuning style, right? So as you can see that these red color, right, they are also indicating using this symbol like as a fire, right, meaning you are tuning these prompts, okay? And the blue, and with this snowflakes symbol here, which means these layers are frozen, right? We keep it frozen, we don't update it during the training process. We are only updating these tunable prompts, okay? So as you can see that, right, so they apply these a couple of tunable prompts for different layers, right? So they can go very deep, right? From layer 1 to layer 2, can even go to layer N, right? So for every layer, they have a couple of tunable prompts, right? So basically kind of follow the prefix tuning strategy, right? So you're adding some tunable parameters, so hopefully you can, have this kind of nuanced control, right? So throughout the entire network, okay? They also present this visual prompt tuning, right, which is shallow. So here they only apply to this first layer, right? So this is your original input sequence, right? So after these, patches, and you go through this patch embedding, and that's your input, the very first input token sequence, right? So here only add a couple of tunable tokens here, and then the rest will stay the same. Okay, so that's the shallow layer. The number of layers you can tune, right? So not necessarily just apply in the first layer, or either you want to apply these tunable, tokens across all the layers. So you can basically decide, okay, maybe I just want to adding these tunable prompts in maybe a first 2 or 3 layers, right? So these can also be something you can experiment with. So then you can see the trade-off, right? If I'm adding more tunable prompts, I have more, tuning cost, right? Because I'm adding more parameters to the network. But this may help you to have better adaptation, right? So you maybe have better performance as compared to the full fine-tuning. But if you add less tunable prompts, right, you have a much cheaper tuning cost, but the performance may not be able to achieve maybe like the full fine-tuning performance. So these are some of the trade-offs. So another strategy is called adapter tuning, right? So this is, again, follows the category of addition, right? So basically, we are adding some parameters in the network, okay? By the way, so I should also mention that during the inference phase, right, because you are adding these tunable parameters, you are essentially increase the model size by a little bit, right? Because you are adding more parameters to the network. So the efficient fine tuning also is only efficiency is only applied in the training process, right? Because you are not fine-tune the entire network. But actually, in the inference stage, you may incur extra computation burden because you are adding extra parameters in your network, right? Because in the inference, you cannot remove these parameters. If you remove them, it's become the original pre-trained model, right? So you need that extra tunable parameters there during the inference so that your model is able to adjust to your downstream task. Okay, so that's something to consider. Especially you also care about, not only about the training cost, but you also care about the inference speed or the inference latency. Then you may want to be careful how much tunable parameters you want to add to your model, right? If you're adding too much, then you will also incur more inference latency. So that's kind of like an inherent downside of this kind of addition-based approach, right? Because you're adding some tunable parameters to the original network, okay? Okay, so the second is adapter, right? So this also have the same idea. Basically, we want to introduce additional trainable parameters to the network. And this paper, adapt idea is introduced in this paper. First, they are also applied to the natural language processing, right? So here is the adapter specific structure of the adapter. And this is the transformer layer, right? So one particular transformer layer. So these adapters are applied after you do the multi-head attention and the feed-forward layer, right, you're adding adapter, trying to change the representation, before you feed into the next maybe layers for processing, right, the next transformer layer. So they also have an adapter after these feed-forward layer. So basically, these feed-forward layer also have a lot of computation there, right, to kind of aggregate the information before and change the representation. So the idea here is that I want to maybe do some small adjustment, okay? So that's why I'm adding an adapter here to make some changes. So on the right side, right, so we can see how the adapter layer, the internal structure, right? So you have basically like a bottleneck structure, right? So here are just very simple MLP layer. Basically, you down project these representation into a lower dimension, right? And usually there's some non-linearity. Then you have another layer, right, to project back, right? So this is called the bottleneck structure, right? So you first kind of down project, then you up project to the original dimension, then you can feed it into the later process. So although this is like, there's like a small network here, but the idea is that, again, this will be only a very small or lightweight network, right? So you won't have a very heavy, like the self-attention, just one very simple, feed-forward network, do the down projection or up projection, and it won't occur a lot of parameters, right? So that's the adapter layer, very simple, basically using this kind of structure to change the representation. Next, we'll talk about a very popular, fine-tuning strategy called LoRa. Okay, so this is proposed in this paper called low-rank adaptation for large language models. Okay, so this is widely used for parameter efficient fine-tuning, and in not only language but also in the vision or vision language model, right? So we can all using these low-rank adaptation strategies to achieve efficient fine-tuning. Okay. So for this LoRa approach, actually falls into the third category. Okay, so it's a reprimerization technique. So first is the some of the intuition, right? So why we can using this kind of low-rank adaptation, right, to achieve this efficient fine-tuning. So in their original paper, the author find that so previous study shows some pre-trained large language models have some low intrinsic dimension, right? So like the representation actually lie in some of the low intrinsic dimension, right? So you don't need a large dimension to represent a very complex representation, and these large language models can still learn efficiently, in this kind of low intrinsic dimension. So motivated this by this kind of findings by previous research, so they come up with this kind of low-rank adaptation. So here are the key idea, right? So we have these original pre-trained model, right? So let's using these attention weights, right? For the transformer, we have these QKV, right? We have these weight matrices, right? So these are the most heavy computation involved, right? So these W0 here are indicating the original pre-trained parameter, right? So this can be trained on, a large corpus of maybe internet crawled text, right? If you're doing LLM, or this can be like image pre-trained model, right? If you're using vision transformer, okay? So we'll freeze these pre-trained parameter W0, and what we will do is we will learn like a delta W, right? So basically another matrix can be added to the original matrix to make some modification, right? So here we have, as you can see here, we have W0 plus a delta W, right? So this delta W will have a low rank decomposition, okay? So before I dive into the low rank decomposition, here, let's just understand, right? So this delta W is basically how you are able to adjust the model weights, right? Because adding something to the original weight matrices to make the changes, right? So you may wondering, right? So if I adding another, delta W to the original weight matrix, right? How does that reduce like the fine-tuning cost, right? Basically, you are adding another full-dimensional matrices to the original one, right? Isn't that have more computation, or maybe the similar as full fine-tuning? So here is where the like the magic of the LoRa comes from, is rather we have considered this is like a single normal matrices, right? Delta W. Actually, you can decompose that into like two matrix multiplication, right? So they are using B and A, and these B and A can have a very much less dimensionality, right? So here, let's say the original matrices, right? W0 has a D times K dimension, right? So here we can actually using two matrices to approximate or to equivalent these W0 here. Is A has a dimension of R times K, and B has a dimension of D times R, okay? So if we're doing B times A, then we can still get D by K dimension, right, as the original W0. But if you look at these two matrices, right, A and B, R can be very, this R indicating the rank, right? So it can be very a small rank, right? So the value of R can be much less than the minimum dimension of D and K. Okay, so these D and K can be like 512 by 512, right? So in the original, self-attention mechanism, right? But the R can be like 2 or 3. Okay, so you can imagine how much of the the dimension has been reduced, right? So you end up with these two very narrow or small matrices, right? So you maybe have like 2 by 512 and these 512 by 2, right? So these are much reduced matrices. So if you are not clear about the rank, right? So just to have refreshed some of the memory from the linear algebra, right? So we have the rank is basically measure, right? So the these independent columns and rows, right, for the matrices. So for how these low rank decomposition is able to control the complexity, right? So if we have a low rank, which means it will only update the model or the weights in a very smaller subspace, right? Because we only updating the matrix like 2 rows or 2 columns, and this essentially you can actually compute how many multiplications are there, right? So for these matrix multiplication A times B, right? So as compared to the original, if you do the full fine tuning, that's going to be a significant reduction in terms of the parameters and also the computation. Okay, so that's how the LoRa is able to reduce the tunable parameters, based on these kind of low rank decomposition, right? These two matrices which has a very low rank. In the later, we'll see how these rank, right? Because these can be a hyperparameter, right? Which rank you want to choose, and how this will retain the performance. Actually, there's some experiment to verify, what is the appropriate rank we can choose to still have this kind of performance and cost trade-off, optimal trade-off. Okay, so now we've kind of understand the internal mechanism, right, of the LoRa, right? Basically, you using this kind of low rank adaptation, right, to generate this kind of delta W as some of the tunable mechanism to change the original weights. How do we do the initialization and the learning, right? So in their original paper, they initialize these matrix A with Gaussian distribution, right? So zero mean univariance. And they simply set the B matrix into 0, okay? So then the original, the delta W, right? So basically is a 0. Then we were using the, back propagation, right? Training the loss. Hopefully, we are able to learn some meaningful adjustment in these two matrix, right? A and B. So one good thing about these is that you can also remove some of the adaptations, right, if you want, right? Because we are adding these adjustments to the original weight matrix. So then if you don't want that, maybe you don't want that adjustment for a particular layer, you can basically remove this delta W. Okay, so that's the basics I just mentioned, right? So basically you can, using these original weight matrix, adding these adjustment, right? These two low rank matrix, and getting a new weight matrix so that the entire weights can be updated. But you can also maybe totally remove that if you don't want to make some adjustment or adaptation for a particular layer. Okay. So in their original paper, so these LoRa layers, right? So essentially you can apply this to every layers, right? To the as long as you have some weight parameters you want to update, you can apply these LoRa layer to that to do some adjustment. But in their paper, they only apply to this attention layer, right? So to this Q, K, and V. So here you can apply LoRa to WQ, and another LoRa to WK, and another LoRa for WV, right? To make those weight adjustment in the self-attention computation. So here I show some of the result, right? So in their paper, they do this using the large language model, right? So here they are using the GPT-3 as the model. The ablation study they've done is, what kind of matrix these LoRa can be applied to, and how this will affect the performance, right? So here, these are different weight matrix, right? So here in the first column, they are using a rank 8. So R is equal to dimension of 8, right? And only apply to these query matrix. And if you only do this kind of fine tuning, and you achieve these parameter, you achieve these accuracy of 17.4, and this particular data set has 91. You can also do other other weight matrix, right? These key and a value, and also this WO is the projection layer. We talk about in the self-attention, right? When you compute these self-attention, then you want to project back to the original dimension. We multiply with this WO here, so you can also apply there. So basically, just some few-fold network. Okay, so then you can also apply to multiple of them, right? So for this particular architecture, right, GPT-3, on these data set, and they found that the most efficient way is apply that LoRa adaptation to this query and value matrix. Okay, so you don't have to apply to all of them, right? So if you want to apply to all of them, you have to reduce the rank to 2, right? Because if you want to have the same amount of tunable parameter, right, 18 million. So this is a fixed, tuning factor, right? So only have 18 million tunable parameter as a budget, then you can make different configurations, right? You can either make a larger rank, apply to one particular matrix, or you can make a low rank, right? And tune all these different matrix. So here one question: why this rank will reduce to 2, right? If I want to apply to different matrix. Anyone? As I mentioned, right, so the total number of tunable parameters is 18 million, right? So if you apply these LoRa to different weight matrix, so the rank 2, so remember, these are our tunable parameter, right? These B and A matrix, right? So A has R times K dimension, B has D times R dimension. So these are actually the tunable parameters we have to tune. Okay, so if I have a fixed amount of tunable parameters and you apply LoRa to different weight matrix, then you have to reduce each of the LoRa layer tunable parameter, right? So the way to reduce that is by controlling the rank, okay? reduce the rank, reduce the dimension of those B and A matrix, resulting to less tunable parameter. Okay, but if you only apply to maybe just one weight matrix, and you maybe have a more tunable budget, right? So that's why you can go to like 8, a higher rank. Okay. But in their so for this ablation study, so they found that using a rank 4 and apply to these two metrics seems to give you the most efficient kind of the trade-off, right? So based on the accuracy on these two data sets. They also did some other experiment, right? So basically, a couple of takeaways is that this LoRa is able to achieve the performance almost as good as full fine-tuning, right? With far fewer parameters, right? So we are only to these very low rank matrix B and A, right? But we are able to achieve very good performance as compared to the full fine-tuning. So maybe one potential reason is that the downstream data set, right, may not be very different, right? You don't necessarily have to change all these, parameters in your network. And also, if you have a less amount of data, right, if you do the full fine-tuning, as we mentioned earlier, it's going to be prone to overfitting, right? So it sometimes maybe even downgrade the performance. If you're using this efficient fine-tuning, it will reduce the overfitting risk, okay? So that's why maybe you will see they also observe, right? On some of the tasks, it even outperformed the full fine-tuning, right? So maybe for some of the tasks, the data is not that significant. So using this efficient fine-tuning only to a small number of parameters will reduce the overfitting risk so that you have a better performance than the full fine-tuning. And for some of the data set, rank 1 is sufficient, right? So basically, you have a very small number of tunable parameters, right? So you only have like a one column. These B and A is just one column and one row, right? So you can imagine how only a very small amount of parameters has been updated, adding to the original weight matrix. Okay. So because of the success of LoRa, right, so it's actually able to achieve very good performance as a full fine-tuning, especially for a large language model. You have billions of parameters, right? You can imagine how LoRa is able to significantly reduce that, tuning cost. So this is a very, popular technique, and people have, based on LoRa and trying to see if there's any potential, improvement we can make build upon this LoRa idea, right, during the low rank adaptation. So there's other variants, right, like the long LoRa, LoRa Plus, and maybe other LoRa approaches. Actually, there's even recently the iClear have a LoRa downright, another paper that is also built on LoRa. So there's a lot of technique you can consider from the how the rank has been distributed, right? So maybe you can have an adaptive rank distribution for different layers, right? So all these things can be tuned and optimized, so you are able to achieve the best tuning accuracy at the same time, lower the tuning cost, right? So if you're interested, you can maybe read these LoRa variants and see if they can be used in your application as well. Okay, and so this LoRa idea can also be applied to vision transformer. So that's exactly some of the vision community has been used, right? Also adopting LoRa fine-tuning in the vision transformer, and maybe make some small adjustment, right? Specifically for the vision transformer. So for this paper, right? So they call this full LoRa. They apply to these vision transformer architecture based on that, right? So on the left side, basically you have these LoRa. This is the original LoRa, right? So you have these two matrices, A and B, right? So they are the tunable parameter. The other things like the pre-trained weights, everything is keep frozen. One small adjustment or change they made is adding a tunable layer norm. Okay, so that's it. So basically you have a tunable layer norm as like additional tunable parameter, combined with the original LoRa idea. Okay. And then this triple AI paper also, using another called this FACT, is another low rank method to reduce the tunable parameter. And they did an extensive experiment on these VTAP 1K data set. So VTAP 1K is basically a collection of 19 different vision tasks. Okay, so you may have a classification, you have different classification tasks, right? So basically 19 different vision tasks. And using this data set will give us a very comprehensive evaluation of different methods, right? Because if you only apply to maybe one particular task, that maybe don't give you the concrete conclusion, right? But this VTAP 1K is a very diverse data set with 19 different vision tasks. So if we test on this data set and get the average performance, it will give us a more concrete or informative conclusion, right? So here, basically, this is the graph showing the performance of different methods, right? So let's just using the full, fine-tuning as a reference, right? So it's basically down here, okay? So you have a lot of tunable parameter, right? So the highest tunable parameter because you fine-tune the entire network. And the accuracy is, the average accuracy across all these 19 tasks is below 70%, okay? And we can also check other, efficient fine-tuning method, right? So you have this visual prompt tuning, right? You have this adapter-based approach. You have LoRa or maybe some other NOAA and this FACT, which is their proposed method, right? So let's maybe first look at, visual prompt tuning, right? So if you increase the tunable parameters, right, the prompt, the tokens, right, you're adding more tunable tokens, you are able to achieve the performance and able to surpass full fine-tuning, right? The average performance can surpass full fine-tuning. If we look at the LoRa here, right, so LoRa is this red triangle, which is right here, is also outperform the average performance of full fine-tuning, right? So that means with this powerful, efficient fine-tuning strategy, we are not able not only gaining the performance, but we are also enjoy a very lightweight fine-tuning cost, right? And we can also look at their proposed, right, this FACT, right, which also has a very high tuning accuracy, right, as outperform the full fine-tuning and even outperform LoRa right here as we compare to this grayscale star. So that's kind of give you some of the basic idea, right? So if you want to select a best strategy for fine-tuning, so definitely LoRa is a very good solution for you to use if you don't want to using any other variants. So LoRa is definitely kind of like a go-to option. But if you want to gain more performance and maybe further reduce the computation or the tuning cost, maybe this will give you a good reference, right? Which one other method you can choose from, okay? So here, just give you a very quick summary from this particular paper, right? So they are, this delta tuning. So basically, they study all these different parameter efficient fine-tuning strategy for language models, and the green color indicating the tunable parameters modules, right? So I'm not going to go through each of them, but if you're interested, you can check, right? So like which method, which part is tuned, right? So they are indicating by this green color, and how many tunable parameters we'll have for a particular method. And their paper also did some very comprehensive experiment. They have some general findings, right? So this is the overall trend they find. So in their experiment, they find that the full fine-tuning has the best performance compared to LoRa, and LoRa is better than adapter is better than prefix, and is better than prompt tuning, okay? So the previous paper, right? So for the VTAB, some of the method is even outperform, the full fine-tuning. So it depends on the data set, the amount of data you have for a particular data set, right? So for this case, they maybe have a large, language data set, so that full fine-tuning still have like the best performance. So this also give you a sense, right? So like what kind of strategy you want to do, right? If you don't have a lot of data, you have very small downstream tasks, then the full fine-tuning basically is your best option, possibly, right? Based on the previous study we have seen. And this is also some of the graph showing you the memory usage, right, for different models, right? So definitely the full fine-tuning, which is the like a purple pink color, right, will definitely have the most memory usage, because you have the most tunable parameters have to tune. And the LoRa adapter has much less, right? So this is just a comparison in terms of memory usage. And they also did some experiment, right? So can we combine, multiple strategies, right? So maybe in the first step, can we do some adapter tuning, and maybe in the later step we can do prompt tuning, or maybe vice versa, right? So they try these different strategies, trying to combine. Different method, right? So they are, do this experiment on the sentiment classification. So you can also try these, different or combination of these strategies, maybe for some of the vision tasks as well. Okay, so here I'll give you some of the surveys, right? So if you really want to dive deeper into this, you can, read these survey papers, right? These parameter efficient fine-tuning for large models, right? So some of them are for the language models, some of them are for the vision models as well. Okay, so you can check out that. And so specifically for this, survey paper, they kind of survey different method under different, categories, right? So you have adaptive tuning, prompt tuning, prefix tuning, these other like specification tuning, reparameterization, right? LoRa, some other branches. So this just give you like what's the taxonomy look like in this survey, so you can maybe go to the right reference. And so all these parameter efficient fine tuning. So we have this PEFT toolbox, right? These basically on the host on the Hugging Face. So I list here. So they have all these different methods has been implemented. So you basically, if you want to using LoRa, then you just have to go here and readily using that LoRa fine-tuning strategy. Okay, so highly recommend you check it out, and maybe if you have some other applications you want to do the fine-tuning, maybe consider these parameter efficient fine-tuning strategy. Okay. Lastly, I also want to talk about our work. We also have work in this using the parameter efficient fine-tuning for medical volumetric segmentation. Right, so how we apply this strategy for segmentation task. Okay. So the motivation, for us to using this parameter, or to address some of the challenge if we want to using parameter efficient fine-tuning, right, for the medical segmentation, there's a couple of challenges here, right? One is all these large-scale pre-trained model. They are usually pre-trained using 2D natural data set, right? Like ImageNet or COCO data set, right? So these are the natural images, right? But in our case, we have this medical images, and it's also volumetric data, right? It's not like a 2D image. So there's a modality gap, right? So the pre-trained model is for the 2D natural image, but for the downstream data, we have these medical 3D images, okay? And a lot of large-scale model are trained for the classification task. Although recently, like we have the SAM, right, segmentation anything model, we can consider as the foundation model for segmentation. But before SAM, we do have a lot of kind of this pre-trained foundation model that is for the classification task, right? You do the ImageNet classification because the ImageNet is designed for classification. But in our case, we want to do segmentation, right, which is pixel-wise labeling. So there's also task gap, right? So the pre-train is for the classification, but the downstream task is for segmentation. So having these two challenges in mind, we want to trying to mitigate these challenges, right, by come up with some of the novel designs for the parameter efficient fine-tuning strategies. So basically, we want to empower this kind of 2D transformer model, right, pre-trained on these natural images to have the capability for spatial temporal feature modeling, right, because our volumetric data is a 3D volume, right, so we want to have this kind of spatial temporal or depth-wise modeling capability, okay? And also, we want to do this in a parameter efficient manner, okay? We don't want to fine-tune the entire model. We want to do it in the parameter efficient way, okay? And this is our proposed method. We call this matte tuning, right? So basically, we using the adapter structure, okay, adapter approach, right? So again, we have to add in some of the tunable parameters to the original transformer architecture. And so but these matte adapter, so this is our new design adapter. And that is different from the traditional adapter, right? So we just, talk about these traditional adapter. You just have like a down projection and up projection, right? A very small amount of parameters, trying to make some adjustment. But for our case, we mentioned there's two challenges, right? We want our adapter to gain spatial and temporal modeling capability, right? And the second is we want to have this kind of fine-grained representation so that it's able to learn this kind of pixel-wise segmentation. So let's look at the specific design, right? So here, one change we have is in these adapter, we're using these 3D depth-wise convolution, okay? So in the efficient network, right, the first class in the neural network design, we've talked about depth-separable convolution, right? So basically, you have this depth-separable convolution, then you have the point-wise convolution. Because the adapter, we also want them to be parameter and the computation efficient, right? So that's why we also adopt this depth-wise convolution design in this case, and to make it more, parameter and computation efficient, right? So we have 3 by 1 by 1, and we also have 1 by 3 by 3. So these are just different kernel sizes for the depth-wise convolution, and because we are consider this 3D convolution, right? So we are essentially kind of injecting this kind of temporal modeling, right? So we are looking at multiple slices so that we can model that correlation between different slices, which is lacking in the original, like a pre-trained 2D model, right? If the transformer is trained on the 2D image, the temporal modeling is lacking. So we want the adapter to kind of gain this kind of temporal modeling capability by injecting these 2D separable convolution, okay? And because we have, another challenge is the task gap, right? So the pre-training is classification, and the task we want to do is segmentation. So as we know, in segmentation, both the global and the fine-grained local details are very important, right? Because especially for these tumors, right? These, multi-class tumor segmentation, a lot of tumor regions are very small region and kind of blending with different tumor type. So we want to have very fine-grained, detailed representation in our representation. So here, to achieve this, we also add another branch, right? So this is the usual 3D separable convolution to gain the temporal modeling, but we also add another branch, right? So which we're using the Fourier transform, okay? So if you are not familiar with Fourier transform, it's basically a frequency domain application. So basically, you can take the image feature basically represent as a global representation in the frequency domain. Okay, so we take that 3D Fourier transform and we do some learnable parameter here, right? So we have this layer, we have the W and the B, the bias. So we learn some of the global feature aggregation, and we do the inverse Fourier transform, go back to the time space, right? So this is the frequency domain, then we go back to the time domain. Hopefully, this Fourier transform is able to help us to learn some global information, okay? That can help the segmentation task. So that's the two novel designs we used specifically to mitigate the challenges we mentioned, right? So one is the lack of temporal modeling, and the second is we want to have some global and local representation together to help the segmentation task, okay? So based on this design, we can add, right? So we can go back to the original, architecture, right? So we have this mid, adapter apply into different count blocks. Hopefully, this will able to adjust the representation. And let's look at the performance comparison. So we compare with these, like the head tuning, right? So basically just tuning the head. We also have the visual prompt tuning, right? So we compare with only have some shallow layer for the visual prompt. We also have the VPT deep, right? So we have all basically adding the tunable prompt in different layers, right, for the transformer block. And we also have other like adapter and adaptformer, other efficient fine-tuning strategy, and this is our result, right? So we can look at this full fine-tuning, right? So which is highlighted by this green. So as compared to this full fine-tuning, right, we are able to have better accuracy, right? So as you can see that the dice and the Hausdorff distance, right, we are able to improve the dice score, right? So the enhanced tumor, whole tumor, tumor core. So all these different tumor type has been improved based on this efficient fine-tuning, right? Even as compared to the full fine-tuning strategy, okay? And a similar, for the Hausdorff distance, right, we want to reduce this metric, right? So, and we are also able to reduce that for this Hausdorff distance, basically a better performance. So that's for the BRATS 2019 data set, and we also did another BRATS data set 2020, and we are able to achieve similar trend, right, with the performance gain as compared to the full fine-tuning. And if you also look at other methods, right, so some method is able to surpass full fine-tuning, right, this spatial temporal adapter, right, so ST adapter. So this is also a very, good method. They were originally used for video processing, right, so that's why you need a spatial and a temporal, right. So that also works here, right, because this is a 3D volumetric data. As I mentioned right earlier, we also want to gain some temporal modeling capability. So this spatial temporal adapter is able to provide that. And they were able to outperform the full fine-tuning. But still, our method, because of the unique design, right, these Fourier transform, all these things, is able to further improve the performance. So that's the performance-wise. Here we also want to check, right, the number of parameters we have tuned, right? So for the full fine-tuning, you have 100 millions of parameters you have to tune, but in our efficient fine-tuning case, we only have like around 18 millions of parameter, right? So only like 17% tunable parameter, okay? And so this is another kind of figure, graphic view, trying to compare, right? So like in terms of the tunable parameters and the accuracy, right? So we have our method, this meta-tuning, has comparable, tunable parameters as compared to some other efficient ones, right? VPT, but we are able to have better performance than the other efficient fine-tuning method. And we also do the experiment on the kidney tumor segmentation, right, on the CT data set, right? CT, again, is a 3D volumetric data set. We also test on the CT data set as well. And this is our performance, right? So again, we are able to outperform full fine-tuning and, on both of the dice, metric for different like kidney segmentation, tumor segmentation, right? And this composite segmentation class. And also, this is the number of tunable parameters we have. Okay. And we also show some visual quality assessment, right? So basically it tells you, right, so how efficient fine-tuning is able to achieve better segmentation quality. So this is compared to the full fine-tuning. And so some of the, tumors, right, we have better performance even compared to the full fine-tuning. Some of them, they are missed some of the classes. So for example, here as well, right, the first one. So actually the full fine-tuning totally missed the red class. So as the ground truths actually have another tumor type, but the full fine-tuning that doesn't pick up that particular tumor class. Okay. So this is another example on the kidney tumor segmentation data set. Okay. Okay, so that's for today. So basically, we've talked about this efficient, parameter-efficient fine-tuning strategies. So this is really useful, when you don't have a lot of resource to do the fine-tuning, and also maybe your data may not be very sufficient, right? So you should definitely consider, parameter-efficient fine-tuning, right? Maybe using adapter or using the LoRa approach, so that you may even gain better performance as compared to the full fine-tuning. But you also enjoy like less, tuning cost. Okay, so that's basically one takeaway message if you want to get out of this lecture, and maybe consider use this in some of the real world applications. Okay, any questions? Okay, all right. So thank you for coming. Then we'll see you on Thursday. Okay.